So yesterday we talked about dealing with significant digits in our calculations. The next step on that is what's known as dimension analysis, which ultimately is just an expansion or a different way of saying converting in chemistry. Dimension analysis doesn't mean really much anything else besides the fact that it is just a conversion problem. As it says, a systematic way of solving problems. You'll find that you can do dimension analysis or converting a number of different ways. The way that I do it is just one method that I use, that I've seen other math teachers use, and I find that that's an important part of doing conversions and or dimension analysis, so that students in the long run do not see it 3 or 4 different ways, that what they see in math is the same thing that they see in science, so that there's kind of everything kind of clicks together, and that the two classes work simultaneously instead of apart or not together. The conversion factors that we talked about yesterday are exact numbers, and therefore when we look at converting to the proper number of significant digits at the end, we do not take these numbers into account when figuring out our number of significant digits. Again, they're exact numbers, such as it has example here, the 1 inch into 2.54 centimeters, or 1 liter is equal to 1,000 milliliters. And it's all based on that per expression. That's the conversion factor or per expression is something that we will bring up later on in the year. We are just kind of getting us started to think about what to do when it comes to converting. We start with some of the units that we would commonly see in the lab. Later on, we'll look at adding some other things into it, such as grams and moles, and then from there we will expand on to a full stoichiometry problem. But this is just one step in the process that we are going to be using in chemistry for dimension analysis and or converting. Looking at the next slide, I'd like to set it up is this pathway where we have our given unit times our conversion factor, which puts the desired unit on top, the given unit on bottom, and that would then give us ultimately our desired unit. That is because of the use of algebra, that these would be can be written as a given unit can be written over 1, and therefore that would be on the numerator, and the given unit would be on the denominator on the other side, and therefore would algebraically cancel themselves out. But in this case, we're not worried about them canceling out. We're just looking at putting them in that setup. Not all dimension analysis problems have this set up in a way so that that conversion factor is just one conversion factor in the middle. And I think that is what a lot of students miss when we look at these, that sometimes your given unit and your desired unit, your ultimate desired unit, might take more than one path. An example of that is if I asked you how many one football field has about 120 yards on it, if you count end zone to end zone, how many miles is that? That would then require you to go from yards to feet, because that is the one of the conversions that we know, and then from feet to miles, because that is the other conversion we know. Meaning in that sort of a setup, you would have two conversion factors to get you to what your ultimate answer would be. And therefore, it goes on a little bit longer, and it does take a little bit longer. But knowing what your conversion factors are, putting together some sort of a path will help out a lot in the end. The couple of things that do need to be looked at is that we will be asked to look at, say, our meters per second. That's ultimately what you're looking at converting into furlongs per fortnight. Those are actual measurements of distance and time. They're not straightforward ones, which for some make it more difficult because they are not your straightforward miles, kilometers, meters, centimeters, feet, yards, whatever it is. What will help you is if you know the conversion between meters and a mile. There is a straightforward one. Those that are in track probably have an unfair advantage that they know what the mile is in track. What does it run? That is actually ran as the 1600 in track, but ultimately the true mile is actually 1609 meters is equal to 1 mile. That conversion should allow you to go from meters to furlongs with some ease. Now, going from seconds to days does require you to take the conversion of seconds to minutes, from minutes to hours, from hours to days, and then from there you can go to the fortnight. So it does require you to take a number of different steps and or paths to get there. So I'll kind of let you work on that before I start the problem and then ultimately give you the answer. Ultimately, if you answered on this one, D would be your answer for that. The mass of an electron is 9.109 times 10 to the negative 31st kilograms, and we want to express that mass in milligrams. There is a straight from kilograms to milligrams pathway to take. I don't like or suggest students doing that straight pathway. I would prefer students taking the pathway of kilograms to grams to milligrams as the pathway to take, because I think it helps out with where everything goes, and therefore kind of breaks it up into much more easier to use numbers. And therefore when you go through the actual process, it's not as big or as bad. So when we would do the process, we would start with what our given is. Our conversion factor, we're going to use two of them, unlike the previous one where we used so many, is the kilograms to grams, because our grams is going to be our want or desired one for at least the first conversion factor. So we write what we start with or what we're given, 9.109 times 10 to the negative 31st. So my kilograms, my desired label is grams for the first one. I want to get rid of, or what I'm given, is kilograms. And then we ask ourselves the question, which label is bigger, kilograms or grams? And that one that is bigger gets the 1. the one that is smaller, then we ask ourselves, how much bigger is the kilogram or over a gram, or whatever that conversion factor is. And in this time, it's 1,000, which, as we'll find, tends to be the most common conversion that we use outside of a million or centi or 100 for centi. So when we look at this algebraically, our kilograms cancels out. We could continue on and write our answers in this space here and continue right along, but for the sake of space, most likely won't get there. So we'll start over almost the brand new thing with the brand new number and write out, which will end up being 9.109 times 10 to the negative 28th grams, and now I will convert that into what my ultimate desired unit is, and that is kilograms, not kilograms, I'm sorry, milligrams, and get rid of just the grams in there. In this one, we ask the same question, which is bigger, a milligram or a gram? Grams are bigger, and there are 1,000. Zero's not working right very well on this screen. And we have 1,000 milligrams in 1 gram. So our grams cancels out. We are multiply that out to get our answer of 9.109 times 10 to the negative 25th milligrams. Next question has us converting from millimeters per second into kilometers per hour. Again, taking that multi-step approach to how many millimeters are there in a meter, how many meters are in a kilometer, will help the process out. This one, just like the one where we had earlier, where we were asked to convert from meters per second to furlongs per fortnight, we have to convert from seconds to hours, but it should be a lot easier from a conceptual standpoint at least, to go from one to the other. And how you do this, again, you can do this multiple step ways, or just putting it together in one long road step. That is my preferred method when we are doing it in class. The medium that I'm using here doesn't allow for that as much. So we would start the problem off as 0.515 meters per second. I'm going to convert all of my distances out. So millimeters on the bottom. Ultimately, I want to go to kilometers, but I'm going to start by getting into meters. And since meters is bigger, it gets the 1. There are 1,000 millimeters in 1 meter. Algebraically, my millimeters cancel out, setting me up to now convert into kilometers, ultimately the distance label that I want. Kilometers is bigger. There is 1,000 meters in 1 kilometer or kilometer. Meters cancel out. I put all that information into a calculator, so I can ultimately take 0.515 divided by 1,000 times 1,000, which is the equivalent of, I believe, 1 million, to give me the answer of 5.15 times 10 to the negative 7th. Now, if you do this as one long stretch where you would be converting to time here over where I marked in black, you would not do your multiplication until the very end. My label for down here now is kilometers per second. I'm going to convert seconds directly into hours, which is getting seconds on top because I want to algebraically manipulate which one. Whether you use H or HR for hours is completely up to you. 1 hour is still there. It's 3,600, so because that would be the equivalent of 60 times 60, gives us that. I multiply across the top and not across the bottom, which would give me that canceled out. And multiply that times 3,600. I get an answer of 0.001854 kilometers per hour. That is the end of Unit 1, Matter and Measurement. I hope that giving you these last slides of notes was very helpful and useful to you as you prepare for the test.